This is Vera Rubin on the upper right here. And her parents were Philip and Rose Cooper. I don't think I've heard them talk about it at the meeting here. But they lived in Philadelphia. They moved to DC when Vera was 10 years old. And when they moved here, they became close friends of my grandmother, who lived nearby, both in Northwest Washington, DC. Philip was an engineer, and he helped Vera make her own telescope. And he took Vera to astronomy meetings. And my mother recalls, and I just talked to her recently, that she remembers Philip helping Vera make a Ferris wheel out of toothpicks. This is all, of course, when she was quite young. My mother remembers taking piano lessons from Ruth. And what I really wanted to say about her parents is, and this is largely from word from my mother, and is that her parents never taught her that there were things that girls couldn't do, and she didn't realize until later in life that there were other people that were making that claim, and it just rang hollow to her because of that. There's all kinds of stories I could tell, but I'm not going to. When I was about 12, my grandmother wanted to buy me a telescope, but she knew nothing about telescopes, but she knew who to ask. And so my telescope gift was recommended by Vera Rubin, and I think Vera was about the age shown in this photograph when she recommended my telescope, which is why I got into astronomy. I took that telescope out to the backyard and got very interested in astronomy. And then my father took me to a meeting. Well, my father worked at the National Bureau of Standards in DC, and Vera's husband, Bob, also worked at the National Bureau of Standards. They didn't work together, but they knew each other. And my father took me to a meeting, a physics meeting in DC, in one of the hotels here, and we bumped into Vera and Bob at the meeting. And Vera, we chatted and caught up with things, and Vera asked me what I had been doing. And I said I was working summers in high school at a radio and TV repair shop. I know the young people think you just throw these things out when they're broken, but in the old days, believe me, people used to get them repaired. And as soon as Vera heard that, she said, you ought to apply for a summer job at Carnegie DTM, which I did. And I mostly worked in the same group that she was in with Kent Ford and Norbert Tennard. And it's been mentioned a few times that they had the so-called DTM image tube, image intensifier, to give Vera a technical advantage in her observations. But the day and age had come when there was a conversion going from the image tubes to the CCD detectors. And they knew they needed to change technology. And they mistakenly thought a guy that knew how to fix TVs would know how to do that. So I worked summers during college as a summer trainee fellow at DTM with Kent Ford, Norbert Tennard, and of course Vera Rubin. And again, I could tell lots of stories, but the thing I really wanted to convey about Vera in this case is, she was off on a lot of observing trips. And she was always so excited when she got back from an observing trip with the data that she got. She would always yell, "Chuck, come in here, let me show you the spectra." And she would just, as you've been seeing them here, she would lay them out on the table and she would explain what she measured and how she did it and what it means. And so it's hard to express to you in words how enthusiastic she was. She loved astronomy, just contagiously loved astronomy. And I talked to her many times about career advice and things. People said, don't go into astronomy. We were asked by the American Astronomical Society to warn people there are no jobs and things like that. And Vera's advice was always, if you love it, do it. So this is on the top left here this is Kent Ford, this is Norbert Tennard, and that's Vera. This is about the time that I was working there. Mike showed pictures of this event in 2013. Again, Norbert Tennard, Vera, and Kent. So one day, Bernie Burke, who's shown here and here, came by for a visit because he used to work at DTM as well. In 1955, he discovered the decametric radio bursts from the Jupiter EO system on the DTM radio telescope in Durwood, Maryland. Did you know that, Virginia? Yeah. Okay, good. And I should have known. We chatted with Bernie for quite a long time in the library there at DTM. And just as he was leaving, Vera said, "Oh, wait, Bernie, you know what? You should bring Chuck to MIT with you." And so he said, "Okay," and that's how I ended up at MIT after being there. So, you know, as has been said, Vera really, it seemed like just me at the time, but I realized that she did this for all kinds of young people, really encouraging and helpful to solving problems, you know, and concerns of young people. Virginia mentioned that George Gamow was her thesis advisor. This is Vera around that time. And that George Gamow also had Ralph Alpher as a student. And of course, you're all familiar with the story of you know, the beginning of the work on Big Bang nucleosynthesis with George Gamow, Ralph Alpher, and then later Bob Herman. In that work was the prediction of the cosmic microwave background should exist. This is just saying there's nuclear reactions going on in the early universe, and there's going to be matter in equilibrium with radiation. And so there should be an afterglow. So the Penzias and Wilson discovery in '65 was you know, obviously a confirmation of that. But I was interested in Bob Wilson's Nobel lecture in 1978, where he said that, you know, lamented that cosmology is a science that doesn't have very many observable facts to work with, and that maybe this cosmic microwave background could be helpful in learning something more about the universe. And I want to emphasize, this was only 41 years ago. 41 years ago, we knew almost nothing. And this was great for the theorists because they could make up anything they wanted, and you know, it could be, right? And so that was how things were. The progress in cosmology has just been enormous. So this has been shown a couple times today. You know, Kobe kind of confirmed the other part of that prediction of this radiation, and that is that it's a black body, the signature of radiation that was in thermal equilibrium with matter at some point. And therefore also confirms the prediction of a hot and dense early universe. This was, in my mind, the first precision determination of a cosmological parameter. This temperature can be viewed as a photon density, or in other words, the current radiation energy density of the universe. Mike mentioned, as people previously do, that there's a 6-parameter model that fits the spectrum. But it's actually a 7-parameter model because this is one of the parameters. It's just so well known, we don't even think of it as a parameter anymore. Thanks to John Mather, it's now a constant of nature. So this was a very important discovery. The Kobe went on to also discover the temperature fluctuations in the CMB, which was obviously important. And then we went on and did Wmap. To observe the same full sky CMB with much higher angular resolution. And the reason that making this map was useful is because we think that we understand, at least to some degree, the physics behind this map. So we take the power spectrum of the map, see how much fluctuation power there is at different angular scales, and then we use the physics that we know of the photon baryon fluid. David talked about this this morning, to fit these parameters to the power spectrum. And in this case, the dark points are the Wmap data, and the red curve is a combination of Wmap data, a higher resolution CMB data, from the time, baryon acoustic oscillation data, and the value of the distance ladder H0. All of that's in there, and you can see that there was a very nice fit. Everything was hanging together quite well. From that, we got this, you know, the famous pie chart kind of thing of the composition of the universe. We got the values of all these parameters. And of course, all of this assuming the Kobe-Firas photon density, or radiation energy density. And as Mike showed a version of, you can take the Wmap baryon density and divide by the Cobe photon density, and you get this eta parameter, which is the baryon to photon ratio, is the only free parameter in Big Bang nucleosynthesis. And this is the Wmap at Cobe vertical line of where we sit on this for helium, deuterium, lithium, using a complex set of nuclear reactions that you have to know cross sections and rates and things like that. So those pictures came from this review article of Fields 2011, the primordial lithium problem, and the point here is that the helium-4 mass fraction in blue from the CMB plus BBN compares well with the light element abundance measurements. Also, the deuterium to hydrogen agrees well. But if you look here to the lithium, it's way off. It's not just a little bit off. And so the review article says it falls short by a factor of 3 to 4, and this is a 5 to 6 sigma mismatch in lithium-7. This mismatch has been there, I don't know how long as I can remember, there's been this mismatch there. So while we often say Big Bang nucleosynthesis is a great success, this is a great failure. And it's still unresolved. In the early days, people said there'd be a zillion different explanations, but little by little, I think they've been chopped away. Reaction rates are well known, more things are included, the computers are better, and all of that, and yet this is at least as much tension as it used to be. So Wmap went from a state-of-the-art of the CMB power spectrum like this, from before Wmap to this. If you think about the 6-dimensional parameter volume, Wmap shrank that volume by a factor of 70,000. And what the amazing thing is that the model, lambda CDM, didn't break in that stress test. So one of the things that at least I feel is that there's something very substantially correct about lambda CDM. It can't be a coincidence that it could withstand this stress test and agree with so many things, and yet say, well, it's just completely wrong. We've already mentioned the accelerated expansion of the universe. As sort of the flip side, the CMB observes the mass energy of a dark energy, whereas this is a measure of the dynamics of the accelerated expansion. So two sides of the same coin. And so now going back to Bob Wilson's point about very few observational facts, well, you sort of knew about those. But since then, we have the spectrum, we have the radiation energy density, we have the anisotropy, we have the accelerated expansion, we have the composition of the universe, we have its age, we even have the fact that there is not equal fluctuation power on all scales, that the universe is consistent with flat, a high degree of accuracy, and that there are adiabatic Gaussian random fluctuations. The last three of these relate to whatever happened in the beginning of the universe, inflation or whatever else. So we've gone from lamenting not having very many cosmological constraints to having quite a large number of constraints. And so this is the great success of lambda CDM and the measurements and the theories that went into things there's a lot about the universe that we understand. But we don't understand everything. We don't understand the lithium-7, and we don't understand this. If you take the Wmap data and combine with finer resolution ACTPol and SPT data and BAO data, which was done in a paper by my postdoc Graham Addison, recently, you get a Hubble constant of 68.34 plus or minus 0.61, and you can compare that with this year's version of Adam Riess's distance ladder, which gets 74 plus or minus 1.4. This is a 3.7 sigma tension, which is not good. So there's the lithium-7, and then there's this Hubble trouble. And then, of course, we had the Planck Emission. Which is went from Wmap's 0.2 degree resolution to 0.1 degree resolution, so it's twice the resolution. and generating a power spectrum that goes out to twice, basically, in the multipole moments. And this introduced measurements of Silk damping scales with other parameter combinations and with CMB lensing. CMB lensing basically smears the peaks, so you have whatever the peak to trough ratio is, it gets smeared out a little bit. I should mention that this additional information took that 6-parameter volume down by another factor of 300, although I personally feel like some of the really exciting stuff from Planck comes not from the power spectrum, but from the map of the CMB lensing potential across the sky and the map of clusters in Centennial-Sildovich across the sky. So one of the big questions was how quantitatively similar Wmap and Planck data were. And I assigned this to my graduate student, Yajing Wang. And I truly thought this would not be hard to calculate, but it turned out to be very complicated, and she really did a great job sticking with it and figured it out. If you want to know why it's complicated, you can read the paper. But what we found, or what she, when I say we, I mean she, what she found was that the power spectra of the two missions are consistent within 1 sigma, but you can only compare them where they both have measurements, up to about a multipole of 1,000. So of the part of the spectrum that they both measured, they are extremely consistent with each other. People I saw were, experts in the field who were saying, well, there's something different between the Planck and Wmap parameters, so one of these experiments has some kind of issue. That's not the case. The overlapping information is the same. So we wrote in the paper, cosmological model differences between Planck and Wmap do not arise from measurement differences, but from the high multiples that were not measured by Wmap. This is a picture that appeared in the Planck papers. Basically, you get gravitational lensing of the CMB signal as the photons traverse the mass distribution in the universe. And I mentioned that it reduces the peak to trough contrast in the power spectrum, but separate from all of this, you also sample the lensing from the non-Gaussian statistics in the map. And so you have 2 ways of measuring the lensing, and this figure compares them to the two in terms of something that's not really a parameter. AL here has a physical value of 1, but if you let it be free, this is what the data prefers. And so they're showing that there's some disagreement between the 2 ways of sampling the lensing. We followed up on that in a paper, again by Graham Addison, by taking the Planck data apart for L less than 1,000 and L greater than 1,000, that is to say more or less the Wmap-like part and the other part. And so the Wmap-like low L part is the red here from the power spectrum, and it crosses the map non-Gaussian measurement at AL equal 1, which is exactly what should happen. But the high L part of Planck and the lensing, L greater than 1,000, really doesn't cross it at all. And it's this tension that's 2.4 sigma at the time this work was done. Actually, the latest result of Planck 2018 makes this worse. It raises this to 2.8 sigma tension in the weak lensing. We also showed in Graham Addison's paper how the parameters vary with lensing amplitude, and you can see if you just look at the AL physical value of 1, you can see for L less than 1,000, Planck gets a Hubble constant of about 69. Whereas at the high L, it gets about 64. About 2.5 sigma tension here. So in this Hubble constant comparison, everything in blue here is a CMB. The Wmap is the top one. There's ACT pole at high resolution, SBT pole at high resolution, and here's the Planck 2015 temperature. But here I've divided again, this time at 800. It doesn't really matter if you divide it at 800 or 1,000 or 1,200. But you can see that this Planck measurement is made up of 2 pieces that have tension with each other. And then this is the brand new Planck 2018 result. And this is a result that has no CMB at all in it. This is the baryon acoustic oscillations, which are normally calibrated by the CMB, but Graham Madison, to make a point here that's free of CMB data, instead used the D to H ratio to get the baryon density to calibrate the BAO. The BAO itself measures the product of the Hubble constant and the horizon size. So you have to break that degeneracy to get just the Hubble constant, and that's what's been done here. So, and these are all to be compared with the lensing time delay measurements. This is the holy cow group, and the Adam Riess's distance ladder measurement. And yeah, I think you can see there's, you know, these two are outliers of the distribution and disagree with these by 3.8 sigma, 4.4 sigma, another 4.4 sigma. So fairly serious disagreements. Now, the size of these CMB uncertainties is driven by what's called the CMB geometric degeneracy, and that can be broken by combining the CMB with BAO. So if I combine each of these CMB data sets with BAO, I can get the green points here. So this Wmap one shrinks to here, and this ACPOL one shrinks to here. You can see all of the CMB ones not only get smaller error bars, but you can see it also aligns them. So the ones that were high move down, the ones that were low move up. I drew a vertical line. This is not a fit. I just drew a vertical line at 68. And this 68 line crosses every single one of those green data points, both the CMB ones and the one that's CMB free. And it's pretty far off of the lensing time delay, and especially the distance ladder. Weak lensing, galaxy weak lensing also has tension. Again, Wmap here, here's Planck 2015, again split into a low L and a high L piece, obviously in tension. Here's the Planck 2018. And then here are 4 different ground-based lensing measurements, which look pretty good with the Wmap and the low L Planck. Of course, those we already know are quite consistent with each other because their power spectra are within 1%. But there's definitely tension going on between the high L part here and these points. And this is another, depending on exactly what you're comparing, this is 2 to 3.2 sigma tension here as well. So what is going on here? And the answer is, I don't know. I think it's very important, though. These are not minor disagreements. And the only way I know to sort this out, other than additional data, is to do consistency tests, such as what we've done in measurement replication. These are critical to doing this. We have to be careful not to build experiments where we only build one of a kind, because a person with one watch knows what time it is, and a person with 2 watches is never sure. Planck, again, Planck low L and Wmap are in excellent agreement. So Wmap replicated the Kobe DMR measurement, which went up to L of 22, and those two are consistent with each other. Planck replicated the Wmap measurements up to L of 1,000 or so. But if you go beyond 1,000 in Planck, you have a series of tensions here. And these are not necessarily independent of each other. These are just different ways of seeing tension. And these 5, which are all around the 2.5 sigma level, are unique to the Planck L greater than 1,000. The tension with the Hubble, with the distance ladder, is more than 4 sigma, and I think is in a different category than the others. And the reason I say that, even though I keep reading in journal articles that it is a Planck distance ladder discrepancy, that's not really true. This is a discrepancy that exists independent of Planck data. I just showed it to you for Wmap, and it's even independent of CNB data at all, because I showed it to you with regard to the BAO. So this is a more general tension that exists in the data. Basically, anything that depends on the sound horizon of the early universe is conflicting with anything that doesn't in our measurement of the Hubble constant. And the fact that that's a physically based statement is very interesting, at least to me. So I want to emphasize that in terms of the current state of cosmology, we're not about to throw out lambda CDM. It's enormously successful. As I said, it survived enormous stress tests. And while the pieces were certainly around earlier, I think that Wmap's establishment of all the parameters in one physics experiment package really gave a lot of muscle to the believability of lambda CDM, but nobody said that lambda CDM is complete. So we all know the meeting is concentrated on the fact that we still don't know what the dark matter is. We don't know what the dark energy is. We don't know if inflation happened, and if so, what kind. We've got this Hubble tension, which I think is significant and maybe end up being helpful to be a clue. The Lithium 7 problem, I have no idea what's going on with that. And then this series of 2.5-ish sigma tensions related to the Planck high L data. That's related to a particular data set. So we've turned an interesting corner in cosmology because Bob Wilson said we knew almost nothing and theorists could invent anything. But you might notice there haven't been thousands of theoretical papers explaining this tension. And the reason for that, I think, is clear, is because cosmology is so well constrained, it's not easy to do anything. And there have been some papers that suggest solutions to the tension, but they have a tendency to leave out some of the data sets that they make worse. So if you actually use all of the data, it's very difficult to invent solutions to this problem. And that is a result of the successes in cosmology of creating the lambda CDM model. One of Mark Kamiankowski's collaborators, Poulin, has one of the more successful models in dealing at least with the Hubble tension. Whether it's right or wrong, I don't know. So the future of cosmology, there's a flood of data coming. I mean, I thought of starting this part by listing all the experiments, but that was way too big a job. But there's a lot of experiments coming. There's a lot of data coming. A lot of it was designed to answer the questions about dark energy, which is something like 20 years old question. Dark matter, which is obviously a much older question, maybe 40 years, depends what you want to count from. And the question of whether there are deviations from general relativity, we've been asking for 100 years. So I remember, I don't remember the GR kickoff, but I remember the kickoff of these other two problems. And they've been around actually a long time now. I do think that advances are going to be hard won because these, to make advances, we're going to have to really control systematics at a very fine level, and that is much easier to say than to do. And I promise that with all this flood of data coming in, there will be conflicts that arise between the different experiments and data sets. I feel fairly confident saying that because it's already the case with the current data. So I want to emphasize again, it's very important to have independent replication. It is not okay to do one experiment and say, well, we know the answer to that. So I'm concerned about whether there'll be independent hardware and groups working on similar overlapping measurements. So what are the sources of the current tension, the Hubble Constant, the Planck high L? Are we building the right experiments to address these questions? These are newer questions than the other one. I hope we don't have the same questions in 50 years. But if the dark energy is really lambda-like, then we could be right, in the same place. We may know it a lot better, but it'll still be unknown. I really hope we know what the dark matter is. That I think there's just so much fabulous work going on in the direct detection, but there's no guarantee that we'll know what that is. The people that do the dark matter direct detection experiments are my heroes because it's really difficult work and it needs to be done. Lithium 7 is a mystery to me. I have no idea what's going on with that. I follow the papers on that every time they come out and read about the advances and see what they say, and they all go, maybe there's new physics. And the H-naught tensions, I see as an opportunity. They may be telling us something important that may help us with some of these other problems, or maybe not. I simply don't know. So I would like to share with you Vera Rubin's advice, which is to be adventurous. Serendipity can be used to advantage. We may trip over things that we're not looking for that help with these other problems. And to maximize serendipity, you would like to, this is not the opposite of John Mather's advice, which I agreed with, of thinking big and bold, but this is something you should also do. I think about small and quick, because we can maximize the chances of serendipitous discoveries that way. especially probing new observational parameter spaces, and especially not letting technical difficulties stand in the way. The reason that things haven't been done is because they're technically difficult. That's a challenge to be accepted. So I want to thank Vera for everything she did for me, which was, as you heard, quite a lot. It got me interested in astronomy, it got me to MIT, it gave me advice over the years. We kept in pretty good touch. A picture of me here visiting back at DTM again. And a couple of her quotes, both of which Aranya had on her biographs, encouraging people to do what she did, which was to just have enormous fun with what you do. So thank you very much.
Before we start questions, which we will get to, I know Katie has to leave in a minute. Is that true, Katie? Yeah. Okay, Katie, would you like to make a final announcement?
Well, this has been an amazing meeting, and one person we haven't thanked enough. One person we haven't thanked enough is Jeff Urbach, who's right here. So kibitzing with us as a condensed matter theorist, this is pretty exciting.
Spectacular.
And thank everybody for coming, and thank all the speakers. And now I pass it to Jeff. You're going to thank local help you're getting here, I'm imagining, so let me hand it to you.
Okay, I'll keep this quick. I did some thanks at the very beginning. I'll thank again our organizing committee, Mark Kamiankowski, Jessica Rosenberg, Ed Van Kuren, of course, Katie. Did I miss anyone? Wasn't prepared for this. And Alicia Weinberger, thank you, who is not able to be here this week. And then Amy Hicks, who provided administrative support to all of this. She's worn out, so she's left. But she knows how much we appreciate that. I want to thank all of you for coming. So first of all, let me say that we're not done. We have two more events. We have the public lecture that Katie and Netta and Virginia, I think, are about to run off to. I'll give you directions for that when we're done with the questions, for those of you who are going to go later. And then tomorrow we will have a session upstairs, 2 floors up, the session starts at 9, but again, we'll have breakfast between 8 and 9. And there we'll be broadening the discussion. We'll start with a keynote lecture from Abigail Freeman, who will talk about the exploration of the Vera Rubin Ridge on Mars. And she's a young planetary astronomer who's a wonderful speaker, and will talk about Vera's influence beyond the field of cosmology as an inspiration, followed by a panel discussion with several of our invited speakers from the last couple of days about issues related to women and expanding the participation of women in physics and astronomy, and then a working luncheon for those of you who are able to stay to come up with ways to move forward. I think that's all I've got to say.
Okay.
Like I said, I'll come back at the very end to provide some instructions
Perfect.
on how to get to the...
So, Chuck, I agreed with almost everything you said about Big Bang nucleosynthesis. But the lithium problem, the hard part in Big Bang nucleosynthesis is inferring the primordial abundances and having a story. So helium was a tough row, but the Big Bang makes a lot of helium, and you can back out what stars make. Deuterium is not made in stars, so that was the clean one. Lithium is really, really hard because stars make lithium, stars deplete lithium, lithium is made in the interstellar medium. And the whole lithium thing started in 1980 with the Speets finding this plateau in cool stars. And I think the most likely explanation is that we haven't determined the primordial. Yeah. There is one good paper, Martina Garbino. If you had a late decaying particle, normally late decaying particles are really, really bad because they'll break up helium and make too much deuterium. But if you have a late decaying particle of just the right mass and just the right lifetime, it'll destroy the beryllium-7 and bring down the lithium. But I really think it's astrophysical at the end of the day. And so I think I agree with 99% of what you said, but I think to put a sigma on it, because there's a big assumption that we've seen the primordial abundance.
So I agree that the abundance measurements are challenging and have uncertainty. Then that could turn out to be the result, but I don't actually think it will turn out to be the result. That number hasn't changed in years, and if anything, it's actually gotten worse.
It's the interpretation, it's not the measure.
But what I observe is that the lithium, because you're going through so many more reactions, basically, and it's a more subtle process, is more sensitive than the others to subtle effects, and I suspect we'll find out that there's something a little more subtle. I also have read about, but don't buy, the fortuitous particle, the right energy to screw up lithium-7 and nothing else. This is just an opinion.
All right, question in the middle there.
Hi, I have a question about your tension plots. So what's
Can you wave
BAO?
your arm because I can't see who's
Here.
talking? Ah, there you are.
Sorry.
Thank you.
I have a question about your tension plots. What BAO data did you use? And is that a combination of high redshift and low redshift BAO? And does it make a difference if you separate the high redshift and low redshift, like high redshift from Lima Alpha Foris and low redshift from
Yes.
Galaxy?
So we've done all of that. We've looked at the Galaxy low redshift BAO. We've looked at the Lyman Alpha BAO. And what you saw on those plots was the combination of them both, but it doesn't really make any difference.
And what data set did you use?
We keep you updating to whatever the latest at any time is. So the thing that the BAO provides that's helpful to the CMB is the matter density. That's part of the geometric degeneracy, and as soon as you put that in, you end up with an omega matter of near 0.3. And that's actually the only matter density where both the high and the low redshift BAO overlap. So you're basically driven to that no matter what you do, which, the BAO data are getting better and better. A big improvement in BAO data came when they stopped doing sort of this volume average effect and just considered separately the radial and the tangential components of the BAO. And that really helped a lot.
And just to say separately that the dark energy survey had a paper which showed that you get a similar constraint with this 3 times 2 point analysis plus BBN, also independent of the CMB and H0, which gets a similar answer to what you showed.
Thanks.
All right. Here.
Speaking of BBN nucleosynthesis and the abundance determinations, the helium abundance is actually not as well known as it needs to be. And in particular, we tend to think that when we use the CMB to put a limit on N effective, that we're looking at the same thing when we are dealing with the photon to baryon ratio at BBN time. And the expansion rate of the universe at much earlier times can be, doesn't have to follow the assumption that N effective is the same in both. There are, models in which they're not. And a key would be to determine the helium abundance better. Right now, there's a 1 sigma preference for a delta N effective, which is not 0. And we've already sort of convinced ourselves from the CMB papers and the analyses that assume N effective is the same at both. That's gone away. That's not gone away.
I all in favor of more accurate measurements, and I would like to see that. I think the current N effective is well within the uncertainty of 3.046, which is what it's expected to be. So, but we have looked at we and other people have looked at the effects of changing a variable N effective with the sound horizon in the early universe. But it's because it's so well constrained by the CMB that it's not a very favored solution.
If I may have 2 questions. So the first one is for both Mike and Chuck, and is if you were to address young researchers, it's related to the data-driven analysis of Vera. If you were to address young researchers, what is the thing that you would suggest to measure at the best among all the things that we can observe in the universe at this time? And the second question is, if you don't have any experiments that can replicate Planck in the next future, what would be the compelling consistency check that you would like to apply to the high-L Planck data in order to be convinced that they are either correct or incorrect?
Yeah, let me take a shot at the second question, which is there are a number of experiments now measuring not the high-L temperature, but the high-L polarization. And the polarization data as a whole is just as constraining as the temperature data is. So I'm at least hoping that as we get better and better polarization measurements, we can use that to compare those parameters against the temperature parameters as at least partial check. But this is part of a plea that while it's true that we've made measurements, very detailed measurements across the whole temperature power spectrum, it really would be nice to replicate that one. And SPT and ACT SPT measures even higher L than Planck does, and but they don't cover as much sky and that sort of thing, so that they're not a good enough check on what's going on, basically. You want to offer advice, or you want me to?
I'm happy. I give a lot of free advice, and it's worth what you pay for. So my advice would be to follow what you think is most interesting. Because I think, either Chuck or I or anybody who's, been around for a while can say, well, I think this is how it's going to go. And you've heard us disagree on the lithium, which is really interesting. And you're going to have to do it. And some people like measuring something very precisely. Some people like wild and crazy ideas and going into a new frontier. And I think that's the beauty of science. It's like a baseball team. So you have different players. You have someone who gets on base every time. You have someone who swings for the fences and strikes out a lot. And so we need all of those different things. And because it's going to be really hard work, it's what Vera said, you have to love it. And so if you love the wild and crazy ideas, do it. If you think measuring that extra decimal place and following up that tiny, I know it's only a 1.8 sigma discrepancy, but something smells bad about it. I know it's going to unravel the whole picture. You should do that, because neither one of us can predict which one is going to be most fruitful.
Right. I was going to say exactly the same thing. And not only can't we predict what's going to be most fruitful, but I agree especially with you need to do what's exciting to you and what you're passionate about, because that's the thing you're going to do really well, because you really care about it. And so it wouldn't be good for other people to tell you which thing to pick.
Well, I think that's a wonderful note to end on.